So the first day again is like more on the theory side. We had like two perspectives with Johanna Wagner and Martin Seber with like high density EEG, mobile brain body imaging approach using all behavioral aspects that you can get in combination with EEG information and source localization, head models, realistic head models, and so forth. Which is like on a very extreme side of mobile brain body imaging that requires a lot of hardware and that restricts behavior of participants to a certain degree. We are now moving a little bit to the other side of that continuum of mobile brain imaging with Sarah basically giving us insights into Android applications of mobile EEG. She's been working on that for some time. I just learned that Sarah is from Oldenburg and basically studied in Oldenburg, did her bachelor and master's there in cognitive neuropsychology, the master, and then graduated with a PhD, an excellent PhD, if I might say so. So congratulations again for that, in engineering, actually. So this is a big feat for a German university, I would like to add here. So with that, I'm very much looking forward to your talk, Sarah, and learning more about what you're working on at the moment. Please, the stage is yours.
Thank you, Klaus. And yeah, thank you everyone actually for stopping by and to actually turn on your cameras. Very nice to see some faces, thanks. And yeah, thank you for everyone logging on from home or wherever you are. I was so hoping that we could meet up in person and that we could see the lab, but yeah, thank you for organizing the lab tour. I think this was a real nice compromise. And yeah, okay, so let's jump right to it. My name is Sarah, and today I want to talk about some, as Klaus already said, some new developments of MoBI and Android. And the program actually says that I'm going to talk about Riemannian artifact correction. So for everyone who's here for that, I'm also going to cover that. So this is going to be a wild ride, and let's just get started. And I hope that I can bring to you some intuition about true mobile data and the challenges that go along with that. So before we start, maybe a few words about me. Klaus already said I have a bachelor's degree. Oh no, he didn't say. I have a bachelor's degree in computer science and I have a master's degree in neurocognitive psychology. And in my doctorate, I combined the best of the two worlds, I would say, and I was developing methods for signal analysis, specifically for EEG, of course. And I was focusing on artifact handling. And yeah, so this is my university. The internet tells me that this is how our campus looks like. And since I have not been there in forever, I can only assume that this is still correct. Yeah, I will find out soon, I hope. But yeah, just kidding, this is our university. And it's a small university in northwestern Germany. And because, or despite, or I don't know, its small size, my university, and especially my lab, is very open for innovative research, I would say. The blurry man here is Stefan Debener, and he's normally not that blurry, but he is normally holding gadgets. So this picture is still accurate, I would say. You will normally find him walking around the lab and yeah, not only holding devices, but actually collecting data. And here he's presenting our go-to setup from a few years ago, admittedly, which consists of a smartphone and a small EEG amplifier that connects directly to the Android phone. And now we have a newer phone and a newer amplifier, but still the setup is the same. On the right side, you can see some of our electrode assortments, I would say. And as Klaus has also already mentioned, we are a bit more flexible with regards to where the electrodes actually are placed and how many electrodes we use. And you see here a mobile cap with 24 channels, but also a C grid, which is placed around the ear, here shown by my colleague Maren. And on the lower right, you see our newest electrode grid, which we call the Phi grid, for forehead EEG grid. And we have developed this with patients in mind that are lying in bed. Therefore, the fixation on the forehead actually, so that you don't have to have your amplifier in the back of your head. That is not always working out. But for mobile studies where people are walking outdoors, the amplifier attached to the back of the head, as you can see with the cap, is actually proving to work really well. And these amplifiers do include some motion sensors that I'm going to talk about later a little bit more. So today we want to discuss some of the advantages and disadvantages of both more density, but this, some of you will now think, yeah, this is not high density. No, it isn't. But some setups with more electrodes and some setups with less electrodes. And we will discuss these with regards to the signal that you can actually record, but also the artifacts that you will record with these setups. And so today, as I was also already hinting at, we have two topics. We have artifact handling and Romanian ASR. And then we have MoBI EEG and our new Android apps. And we are going to start with this guy over here, where I hope to give you an intuition about one specific artifact correction method, which is called ASR, and my adaptation, which is called Romanian ASR. But before we look at data, let's have a more like almost philosophical discussion about artifacts. So artifacts, signal or noise. The meaning of the word artifact in signal processing generally means outlier, unwanted signal, or deviant. And with deviant, we normally mean deviating from whatever normal or wanted signal that we want to capture with our setup. But it is very important to keep in mind that this definition is highly context specific. And think about eye-blinks, for example. Eye-blinks present themselves as huge, albeit relatively easy to correct artifacts in EEG. They can be very annoying, but they can also be an elegant input signal for a human-computer interface. And therefore, I think it is important to raise the awareness that one researcher's signal can be another researcher's artifact and vice versa. So what you consider artifact is actually really context specific, and we will later see how it might be beneficial to add some of these signals that we normally consider artifacts to our EEG processing pipeline to add context to whatever we're doing currently without having any markers in the data. So yeah, briefly, I mean, I think I'm really preaching to the choir here. You all know that, I guess, but just to recap, what are the types of unwanted signals or artifacts in the EEG? Really, from zooming out very far away, you can say we have biological or technical artifacts. And biological artifacts are heartbeat and also eye movement and so on, also movement, while technical artifacts are something like a misplaced electrode or you walking through some electric noise field. And this can also be cable movement and so on. Both groups of artifacts can hinder the interpretation of EEG signals because they typically have a large amplitude, while the EEG, as you all know, has a very low amplitude or low signal to noise ratio. And very important in addition is to know that these artifacts, technical and biological, should be handled very differently. And different methods perform differently well with these artifacts, which has to do with their statistical properties and also whether they correlate or don't correlate with the EEG signal. You can imagine that, for example, the change in heartbeat might actually correlate with a task that you are presenting your subjects. So every response that you record in the EEG might actually go along with increased blink rate or increased heart rate. And the same thing is not necessarily true for technical artifacts, but think about cable movement while walking. So cable movement while walking will be correlated with your task, probably. And it's just important to think about these things. And today we're going to talk about a method which does not make assumptions about the origin of the artifact. So it doesn't really care where does it come from, but instead it is actually looking at precisely these statistical properties and whether the artifact correlates with your EEG and on which channels and how many channels more specifically you capture the artifact. The method that I want to talk about today is called artifact subspace reconstruction, and maybe you have heard of it. It is an online artifact handling method that seems suitable for mobile setups. It has been around for quite a few years. It has been developed by Christian Pote and Tim Mullen in the SWAT Center for Computational Neuroscience in San Diego. And this has been some time now. But for many years, I would say it was met with skepticism in the EEG community. At least we didn't really find much literature actually exploring or using ASR. And one of the reasons might be that there was no validation paper out. In the truest form of the SWAT Center for Computational Neuroscience, they put something out there and then it was just there, but they didn't really publish any validation or much documentation for it. And also, it is quite a complicated method. So it's not really intuitively clear what ASR does and whether it's a good idea to actually use it with your EEG data. Yeah, but we thought that it might be worth investigating, and therefore we did. And during this investigation, a point of improvement arose, which we followed up, and we called it Riemannian ASR. And I'm going to walk you through original ASR first, and then I'm going to cover a bit of my adaptation. All right. So first, when talking about ASR, I find it important to actually distinguish the ASR Toolbox, which is included in EEG Lab, and the ASR core algorithm, which is in fact only part of the Toolbox that is integrated in EEG Lab. When using the Toolbox, many more functions can be used that I have listed here in gray, and clean ASR in bold is really the core algorithm where ASR is located. And therefore, if you use the Toolbox, many more things can actually be done with your data offline, by the way, because not all of these methods are actually online methods. So not all of them work iteratively using data as you record, but some of them require the whole data set to be finished before actually using the method. So keep that in mind. We are today only talking about the ASR core algorithm. And ASR is an online method, meaning that it needs to be trained or calibrated. And then after the calibration phase, using normal artifact-free EEG data, it enters a processing stage, which is the second phase of the method. Yeah, when you use the Toolbox with all of your recorded data available, it might not be immediately clear that ASR is actually a supervised method. And when people do not know that, or it is not made clear to the user, I would say, and when you don't know that, you might not pay attention to what the method actually learns from your data. And it will look for adequate training data in your whole recording. But if everything is highly contaminated because you are working with the MoBI EEG data set, then it might be that the training data is actually not really the best data that you could use for this method. This is important to keep in mind. And I'm going to discuss later on what good training data actually means. Okay, but before we go into the usage, let me give you a little bit of background. And I know this might be a bit too technical for some of you, but I hope that you get the intuition, because there's a lot of mathematics, but I don't think that you actually need that much mathematics to understand what ASR is doing. So first of all, ASR detects artifacts by considering the correlational structure over all channels. And on the next few slides, I want to give an intuition on what that actually means. Consider an eye blink that you see here. This is the map of an eye blink, which is actually captured mostly on the two frontal channels, and then not very much by all other channels. And if you, all right, so yeah, if we look at this map here, you can actually see that most of the channels do not really pick up something interesting, but only the frontal channels do. And to this artifact, we want to come back soon. But before, I want to show you that ASR is actually looking at correlational structure of all channels all the time, not only during an artifact, but all the time. It is computing how similar are the different channels. And most of the time, and this is an oversimplification, but most of the time, not much interesting stuff is actually going on. So to produce this plot, I took 1 minute of EEG data, simulated EEG data, and I computed the correlation between every single channel, the spatial correlation between all channels. And you see every dot here is one of our 24 channels from a MoBI EEG cup. And every blue line indicates a positive correlation. And you can immediately see that the structure is beautiful, but very boring. So there's not a lot going on. Every blue line has the same strings, the same blue color, and there's not much going on. Because normally, if we don't pick up an interesting event, an ERP or an artifact, all of the EEG channels are highly correlated and pick up about the same signal. Again, this is an oversimplification. And what I did now is that I added the eye blink artifact that I showed you before to my simulated data. And you can immediately see that these three channels here, this is FP1, FP2, and FZ is located up here, but also a frontal channel. You can see these guys here, they actually pick up the eye blink artifact. And all the other channels are unaffected by the eye blink artifact, which results in the correlational structure being broken right now. So these three frontal channels are still correlated positively with each other because all of them picked up the eye blink with the same amount. But all of the other channels, they didn't really see the artifact at all. And so the correlation of the frontal channels with all the other channels is now a negative correlation. They pick up a reverse signal. And so you can actually see, I hope, that this locally captured artifact breaks the correlational structure of the channel, of all the channels. And this is actually what ASR is exploiting. So it is not looking at what is the kind of artifact, where does this artifact come from, where is this source localized, is this a technical artifact. It also doesn't compute some important or complex statistical representation. It merely looks at the covariance matrix across all channels, and then it looks whether there is some locally captured artifacts that breaks the normally boring correlational structure. And this is well, of course, this is an oversimplified assumption, but actually it is true that most artifacts in EEG are captured only by a few channels and not by all of them. And you can now maybe directly think about the fact, if I just remove suddenly the whole cap, maybe ASR would not even detect this artifact, and that I have never tried it. But since all of the channels will then again record the same thing, this really dramatic event, when recorded by all channels at the same time, might actually not be detected by ASR. But this is not true for normal EEG artifacts. If you think about eye blinks, if you think about movement artifacts that we saw in Martin Seber's talk today that show peripherally at the bottom of an EEG cap, or if you think about muscle artifacts from chewing or talking, these are all artifacts that are captured very locally on only a few channels. And ASR will actually detect all of these artifacts very reliably. Okay, so let's stay with this correlational structure a little bit. And now I will show you how ASR is trained. So since ASR is an online method, the correlation is not computed once, but it is computed over and over again over subsequent windows. And this is what you see here now during training. We see the correlation between two channels here, and it doesn't matter what channels. And the axes show the variance on channel X1 and X2 and the covariance or the correlation. And every single dot is a covariance matrix computed between these two channels. And over time, you see that most points form a relatively dense neighborhood in this center section right there. But you also see that there are two guys at the right hand of my plot that could indicate an artifact because they do not fall into the same region. And this is maybe not intuitively clear right now, but this is just another depiction of what I showed you before, that if you compute the correlational structure on boring EEG data, you will find the same results over and over again, no matter in which data space you actually represent the data. But if now something interesting happens, then it can be indicated by points falling outside of your normal region, outside of your artifact-free region that the method learns during training. And I have marked these 2 points here. The neighborhood is formed using the clean training data, of course, and normally not only with 2 channels, right? But normally you would use all of the channels at the same time. And if you do that, what ASR is actually doing during training is that it defines a threshold and excuse my weird drawing here. Of course, it will not find a line across all the data points, but it will define some sort of threshold. And it doesn't matter today how this threshold is actually defined, but it is important to actually remember that during training, a neighborhood is defined representing normal data, and everything falling out of that neighborhood, everything being far away, is considered an artifact, no matter what that might be or where on which channel that was actually captured. And for more channels, this space now would not be a linear space, but this space would be a curved data space. And I will now show you what that would look like. So bear with me, this looks complicated, but it's actually very simple. So EEG covariance matrices are symmetric positive definite matrices, that's the name. And it doesn't really matter what that means now, but the important thing is that these covariance matrices form a curved space. And what that means for the ASR method is the following. This picture shows now again the variance between 2 channels. And every data point here, every gray point again, stands for one covariance matrix computed from these two data points. And you see in orange, the Euclidean distance, the way that using normal distance matrix metrics that you also learn in school, right? We learn in school the shortest distance between 2 points is a straight line. Yes, that's true if we have a straight data space. If we do not have a straight data space, this is not true anymore. And let me give you a real world example. If I tell you now, please give me the distance from here to Sydney, you could give me the distance through Earth. But as long as Elon Musk is not finished with his boring company, this is not really a helpful distance, right? We cannot travel through Earth to Sydney. We have to go across Earth. We have to take a plane and we have to follow the rounded space that Earth actually defines for us, so that the true distance to Sydney, at least for all our real lives, is much longer than the distance through Earth. And this is the same thing when using Riemannian distance. Think Riemannian distance takes the true distance between 2 points in this curved data space, whereas Euclidean distance does take a shortcut. It just says, these points, they look close together because I can't find a straight line between those 2 points. But actually, this straight line is not really what helps us when dealing with the data. And if you think about this picture here, again, if we want to say, how far away are these data points indicating an artifact, then Euclidean distance, what was used in original ASR, might underestimate how far these points are away, whereas Riemannian distance will find for every single data point a more precise distance to how far is it away from our normal data space. Yeah, okay, so I know this is a lot, but I hope the intuition makes sense. Yeah, okay, so I read about this curved data spaces and that ASR was using these covariance matrices, and I thought, okay, it might be worth investigating whether the addition of Riemannian metrics, Riemannian geometry would actually benefit the method, and it turns out it did. I added Riemannian methods to ASR, and we were actually able to show that with this more accurate geometry, Riemannian ASR outperforms ASR, and both by means of processing time and performance. And yeah, let me show you some results. Well, last year I didn't publish a paper because I did my thesis, so this data is now 2 years old, but still, of course, relevant. I want to show you what we found. Here you see data containing an eye blink again, and you see the same topography here. And in the time domain, you see a huge eye blink showing itself with beautiful large amplitude. Every single gray line is a subject, and the bold line is just the group average. And this just looks like an eye blink. And then look at these two plots here. The middle plot is ASR, and the right plot is Riemannian ASR. First of all, notice the order of magnitude. So if you zoom in a lot, like here, you will find the shape of the eye blink artifact actually contained in most participants. And you will also see that for some participants, both ASR as well as Riemannian ASR didn't really correct the artifact just as well as for others. And this has many, many reasons that we're not going to discuss today, but just something to notice, I guess. The second thing to notice, and that is actually very important, is that original ASR did contain the spatial distribution of the eye blink. Look at the topography, which looks almost the same as the topography of the raw EEG, just in smaller amplitude. But the isometric lines you see, they have the same form. And with Riemannian ASR, we didn't find that. Instead, we found something that looks an awful lot like a blink-related potential. We didn't follow that up. We didn't have a hypothesis for that. We just observed it, we reported it, and I did not have time yet to investigate it further, but it's very interesting that the spatial distribution of the eye blink actually was changed by Riemannian ASR. And this, of course, could indicate that Riemannian ASR did detect the eye blinks more reliably than ASR. Okay, and so whenever you look at an artifact correction method, it is actually important to not only look at sensitivity, but to also look at specificity. Because if we wouldn't do that, we could just now, I could give you a hackathon task and tell you, all right, you now go ahead and design an artifact handling method right now. And you could be done in 5 minutes. Because what you could just do is you could take the data, remove everything, and end up with a flat line. Then, ta-da, all the artifacts would be gone. But at the same time, I mean, with this simple example, it's immediately obvious, all the interesting signal will be gone as well, right? which is what you look at if you look at specificity. And oftentimes in the literature, you don't find both analyses. You very, very often, you only find the sensitivity analysis, which I think is always something to be at least curious why this is. Yeah, and here you see a visual evoked potential, and I open or I show you all the plots at once because the main message is that we don't really see a difference, and we did not compute statistics, base statistics that test on similarity, but we were happy enough to see visually and to also yeah, confirm that the topographies look the same or almost the same, that we don't find a reduction in amplitude. That was really what we were looking for. So that was a very important result, and I did not bring today the computing times of Riemannian ASR, but Riemannian ASR did not only perform better in terms of artifact correction, but it was also quicker than original ASR. So maybe you want to try out later on. Okay. And yeah, many of you might know ICA instead of ASR, might be more familiar with ICA, because this has been around much longer, of course. And here I want to just give you real quick a highlight on a paper that we have been publishing also last year from my friend and colleague Nadine Jacobsen. She's also here today in case you want to ask her something tonight, maybe. And yeah, she recorded data with 64 channel EEG cap while people were walking on a paved walkway, so an even surface, and then on the lawn. And people were holding a tablet and they were doing some button presses because, again, we wanted to look at sensitivity and specificity. So people had actually also a task to do. And what we did in this paper is we computed or investigated an artifact footprint, which means that we describe the features of what we call the movement artifacts. So often in our community, we hear the term movement artifact, and I'm not sure whether we mean, every time we mean the same thing with that, because the movement artifact can be the muscle artifact from the neck. It can be cable sway by movement. It can be maybe the head that moves in space while we walk. So movement artifact can be all sorts of things, which is why we followed up, of course, groups Ferris, Norden, Wagner, and Seba, of course, but also what Klaus Kramer is doing and many others. So this is just a small subset. There's a lot of literature out there. So we wanted to really describe this movement artifact a bit more objectively. And we came up with some dimensions. I don't want to go into details today. You can actually read that up. But the important point for us today is that you can see that every single dimension of our movement artifact was more pronounced before artifact removal than afterwards. And it didn't make a difference for our data set using our ICA, whether we use ASR alone or ASR and ICA together, which I think is a very beautiful and promising result, because ASR is often considered as a, I would say, pre-processing method for ICA. And while that works out very, very good, my message today is that you can also use ASR alone on its own. And since it's an online method, it might actually be worth investigating. So yeah, my message today is it depends whether it works out or not. It depends on many, many things. And therefore, let's have a quick discussion on ASR before we move on to the Android stuff. So yeah, the main and most important point is training data makes all the difference. So you can imagine if you have overall a highly contaminated EEG data set, that ASR can only work with what it's got, and what it's got to train your normal region will contain a lot of artifacts. So ASR will later on in the processing not detect these artifacts contained in the training data as being deviant. It will say, oh yeah, I have seen this before, this normal data, let's keep that. And the same is true if you calibrate the method without your EEG response of interest, actually. This is something that we are investigating right now, but it might make sense to include your EEG response of interest in the training data instead of having resting EEG where nothing is happening. Because then ASR gets the chance to actually learn your EEG response as well and not find it later on to be, ah, what is this? This looks different than the rest. Let's correct that out. That could actually happen. And then I was hinting at that global artifacts are not detected very well by ASR due to the fact that the correlational structure over channels is contained if the artifact is captured by every channel the same. And then, of course, you will add a processing delay to your pipeline because this is an online method. And I think the default window size is 50 milliseconds or something. But that depends, and actually it might make sense to have a little bit longer processing delay and then enhance the detection, but that's something to investigate. And yeah, the spatial coverage of channels, you would think it makes a difference, and I would think that too. But we did try ASR on C-grid data, which is the thing that you put behind the ear, and it worked out very well. And we are currently investigating that as well, how many channels you can actually take away from your spatial coverage before ASR, say, breaks down. So how many channels it actually needs. And it might be surprisingly little channels. So if you don't really rely on source reconstruction, then be bold and have fewer channels, because sometimes that is enough. And yeah, and if you want to try out all of these things, you can either try it out directly in EEG Lab, and you just have to click this checkbox that I highlighted there in red to add the Riemannian distance metric instead of the Euclidean. And all of the other things, as I said before, are additional methods. So just play around with it and check out the source code if you want. I give you in the end my GitHub URL, and there you will find the source code of Riemannian ASR and my paper, of course, these slides and everything that I've talked about, you will find in that repository. So, right, we're halfway done. And as I said, we have two topics today, and we covered the more theoretical part. And now for some more hands-on, I guess. So let's go this way. What I want to cover in the second part are two things. The first thing is just a very brief introduction into lab streaming layer, in case some of you don't know it, because then many of my arguments don't make sense. And the second thing is something that actually Martin Seeber was hinting at today already, that sometimes if we have continuous data, so data of people walking around or even performing a task, if you have no markers to actually add context and information to your data, it might be very difficult to analyze your EEG data later on. And there are many ways around that. And one way I want to discuss today, which is to add other sensors, such as motion or movement sensors, to your EEG using Android apps. Okay, so this picture I stole from Klaus Gramann, because I find the official LSL pictures to be not very good. And while this is a little bit busy, I think it delivers the message. And the message is that there are two sides for the lab streaming layer framework to work. First of all, the lab streaming layer framework is something that you can use to connect all of your devices to a local network, so that you have data access from all of your devices at the same time. And this local network does not need to have an internet connection. So it can actually be used for data protection, the data that falls under data protection laws and so on. And you see these two words. On the left side, you see data sources, and this can be EEG amplifiers, sensors, but also, I don't know, a camera, for example, or eye tracking stuff, and so on. And all these devices send their data to the local network, here indicated by the cloud. And on the other hand, you have receiving systems, and these can be viewers, of course, but more importantly, these can be recorders. So for example, the lab recorder for Windows, but these can also be directly consumers that take in the data that is currently available and run some analysis while you are measuring, like in a BCI, for example, or any other online system. And the lab streaming layer has a new documentation set up at readthedocs.io, and I find this to be very, very good. You have to dig a little bit if you want to find what you're looking for, but check that out if you want to have more information on lab streaming layer. Okay, so the second topic that I wanted to discuss, and actually the topic where LSL helps us and makes our lives easier, I guess, is the topic of markerless EEG. And by this, I mean EEG where you don't really have the option of adding markers yourself. Consider a lab scenario. There we can define events that the participant sees or hears or perceives. And for every event that the participant hopefully pays attention to, we can create a marker that we record together with the brain response. So later on in our analysis, we can actually say, here was the tone, here was the picture, and hopefully if everything is synchronized, we can make sense out of our EEG responses. But now consider this scenario here, where my friend and colleague Bojana is walking outdoors, pre-pandemic obviously, and here we do not have the luxury of creating an environment. We can't control what she's seeing or hearing beyond what we are presenting on our smartphone, which might not be that much. And she will perceive and hear all kinds of things, and we do not have control about the environment anymore. And yeah, as I highlighted in the beginning or hinted at, there are some ways around that. And one is to add sensors to your measurement. And we have 3 Android apps that I want to discuss today. And the first one is actually not developed in the Stefan Devener group, but it is developed by my colleague Martin Bleichner, who has his own group. It's called NEVI. Check them out. They are doing very cool things with mobile EEG currently in the home office or the office environment regarding noise perception. And what I want to present here is the addition of sensors to add information to ongoing EEG. And the sensor in this case was a microphone, in addition to the EEG, of course. So you see a participant wearing an EEG cap, and you see some raw audio that they perceived during different conditions. Doesn't matter what now. And you see here that the audio of the microphone was actually used to compute a set of features. And the most important set of features that I want to highlight here is the onsets. So the onset of every single loud tone that this participant was hearing will be added to the EEG directly, time synchronized, so that you know, oh, all right, I don't know what they were hearing, but I do know something interesting happened here. And importantly, all of these things were happening on one phone. There's no computer in the loop. We did not do any further computation, but everything that they did is done actually on one Android phone. And the audio feature extraction app is what they will present on the book next week, I think. So they have a poster, so check that out. And also this paper with that title, of course, is currently under preparation. And as soon as that is submitted, go check it out. It's very interesting. And so they use this audio feature extraction app and the smarting amplifier, which connects directly to the small amplifier that the participant was wearing. And all of the data streams, so the onsets, all the different features, and the EEG and the markers were recorded by an app, which you see in the center here, which is called Recorder. And this is one of the apps that I want to show you next. So I want to show you 2 apps, Recorder and Sender. Those are 2 Android applications, and they enable completely mobile lab streaming layer setups on Android. And as the names actually suggest, Sender sends out LSL streams and Recorder records LSL streams. And yeah, let's first of all look at Sender. Sender will detect sensors integrated into the device. And these sensors can be very different depending on your device that you have. This can be an Android smartphone, this can be a smartwatch, a tablet, every mobile system where an Android operating system actually is running, you can use with this. And currently, these are the sensors that are included in our app. But any other sensor works exactly the same way. So it will detect all the available sensors, and then it will create LSL streams for every single sensor. You can even use microphone. By now, location and camera is not implemented, but we are working on that. And we had, this is a bit too technical for the current talk, but we did have quite some issues with the sampling rate. So in case there's anyone in the audience that can tell us or help us solving this problem, and if you have any experience with sampling rate of motion sensors in Android, go reach out. And just to capture very briefly what we had is that the Android system will actually, on a whim, change the sampling rate of all the sensors integrated in the phone, which is really painful when you want to record these sensors as time series alongside your EEG, which of course has a stable sampling rate all the time. So yeah, we did find a way around it. So now we have a stable sampling rate, but I did not find the most elegant solution. So feel free to please reach out if you have experience with that, or if you want to know more, of course. So yeah, it seems a little bit boring, I would say, at first glance, but actually think about what this really enables you to do. So in case you don't have the funding to buy more sensors, or in case you want to record truly mobile EEG and you want to know with your audio, you want to actually listen to what people were perceiving during your recording, You can now do that just simply by using one smartphone. You can strap that phone to the leg, and then you can actually detect movement. You can strap it to the head to know where they have been looking, and so on. And all of these things only with one smartphone. So I think this is really great. It has been missing in the MoBI community, I would say. And the second thing is actually more complex, but even more straightforward to explain. So Recorder, as the name suggests, records every stream that it sees in the network. And we did not, this is essentially the lab streaming layer for Android. And we did not change the LSL libraries at all, except for the user interface, as you can see. So we didn't want it to look as the Windows app, but we wanted it to look like an Android app. And therefore now it looks a little bit different. But the core, the underlying libraries is exactly the same. And the XDF recording that it produces from all the streams that it finds is actually exactly the same that you would find on PC. So yeah, I can already tease, so I won't get into detail too much here. This paper is in progress and I should be writing right now, you know, the struggle. But yeah, let me tease one of our validation setups. Here we recorded the same data with Recorder on the phone and with Lab Recorder on the PC. And again, the PC is not necessary for the setup. This is merely a validation device now. So we send out some data streams with sender, we record it with Recorder, we record it with Lab Recorder on the PC, then we compare the two files and we expect and actually find that these files are very similar. Yeah, so they're essentially the same. So all good, and it looks very good. And as I said, this will be open source as soon as the paper is published. So yeah, go ahead and download that and then record data. Yeah, this is the last validation. We wouldn't be the dev in the lab if we wouldn't do a timing test. If you have ever seen a presentation of our lab somewhere, you will know that we do timing tests and other validations, like on and on and on. And I even did them more than actually recording data from humans in my PhD. So yeah, I want to share this timing test with you because I like the setup so much. And the credits for this creative setup actually go to Tristan Stenner, who is an LSL developer. So that was not even our idea, but I like it so much that I wanted to share it with you. So he came up with this brilliant idea. In gray, you see a keyboard from a PC. And of course, you see the phone. And we have two LSL apps running at the same time. One LSL app is running on the PC, which creates LSL markers for every single keyboard input that it detects. And on the phone, sender is running and streams out the sensor data from the accelerometer sensor. And in the test, I hit the keyboard with the phone repeatedly. And every single hit will create two responses. First of all, the marker from the keyboard. And secondly, the sensor response from I have hit something very badly. And these two responses should occur at the same time, ideally. So they do, in fact, in real life, they occur at the same time. So they should be recorded at the same time if our timing is correct. And yeah, here I show you some of our, I don't know, hundreds of trials that I did. So I'm not a robot, so not all of them look the same, but you get the idea. In dashed line, you see the marker, and the blue line is the response from the sensor. And if only EEG responses would look that neat. Like, I know they don't, but here you can actually see, okay, there's the response, there's the response, there's the response. So very easy, yeah, very easy analysis. And the timing looks good. So here you see all timing test trials, and you see this yellow line just forms a straight line. If we had any timing issues, this would be more wobbly or drifting to one side. We don't find that. We find actually that our timing was on fleek. So all good. All right, yeah, so this is already the end, and my take-home messages, I guess, are that artifact correction is important. Do it, think about it. No matter what you do something. Know your data and add information to your data. The more the merrier. Whether you need that in the end, you can decide later, but we find ourselves collecting data over and over and over again, because we do forget that in the end, now we don't know again what were people actually doing here. And this is such a hustle. So yeah, think about it before. And don't be afraid to go completely mobile. So you don't need a PC anymore. That's past. Now the future is there. Okay, so it's a little bit silly, but you know what I mean. So you can actually go completely mobile if your EEG setup allows you to connect with Android. And yeah, try it out. It's very powerful stuff, and it's a lot of fun. And yeah, just thank you to all the people that have been working. There's just a subset of people that have been working with these things, my lab, but there are tons of people missing, you know how that is. And I was mentioning before, find me here, find me on LinkedIn, GitHub, Twitter, ResearchGate, of course, and everything that I showed you today, I will upload in my GitHub. These slides, the talk will be made available on YouTube. You'll find all the source code for Romanian ASR and the Android phones, everything on GitHub. And I am this granny here on Gathertown tonight if you have any more questions. Thank you. That's it.